All right, next let's consider the possible scenarios that can occur when drawing conclusions about hypotheses using data. So the first case is that the true state of nature is that the null hypothesis is true. The conclusion based on the data is that we conclude that the null hypothesis is true. And so in that case, where the null hypothesis is true and we conclude that it's true, then obviously we have come to the correct conclusion. Now the second case, the true state of nature is that the null hypothesis is true, but based on the data that we obtain, we conclude that the null hypothesis is false. So if the null hypothesis is true, but we conclude that it's not true, then obviously we have come to the incorrect conclusion. Now, this type of inferential error is called a type 1 error. All right, now when we say error, that doesn't mean that we've made a mistaken calculation or something like that. What it means is that even though the null hypothesis is true, we have gotten a hold of a data set that has led us to the wrong conclusion. So that situation is called a type 1 error. The third case, the third possible scenario, is where the null hypothesis is in fact false, but based on the data that we obtain, we conclude that the null hypothesis is true. Or another way to say that would be, the null hypothesis is false, but based on the data we obtain, we fail to conclude that the null hypothesis is false. All right, and so obviously if the null hypothesis is false, but we conclude that it's true, then we again have come to an incorrect conclusion, and this type of inferential error is called a type 2 error. So a type 1 error is when we reject a true null hypothesis. A type 2 error is when we fail to reject a false null hypothesis. And then finally, the fourth possible scenario, there are only four. This is the situation where the null hypothesis is in fact false, and based on the data that we obtained from the population, we conclude that the null hypothesis is false. So if the null hypothesis is false and we conclude that it's false, then clearly we have come to a correct conclusion. Now, another way to organize these four possible scenarios is using a two-way table. And so I've got this slide here in the slide deck, possible decision-making outcomes. The columns correspond to the true state of the null hypothesis. The null hypothesis. It's either true or it's false. The two rows in the table correspond to our decision about the null hypothesis. So either we decide that the null hypothesis is true, in other words, we fail to reject it, or we reject the null hypothesis and conclude that by concluding that it's false. So those are the two possibilities for the true state of the null hypothesis, and the two possible decisions based on the data lead to four possible decision-making scenarios. So again, if the null hypothesis is true and we conclude that it's true, then we have come to the correct decision, the correct conclusion. On the other hand, if the null hypothesis is true, but based on the data that we've obtained, we conclude that it's false, well, that is an error of the first type. It's a type 1 error. Now, if the null hypothesis is in fact false, but we get a hold of a data set that leads us to conclude that the null hypothesis is true, or in other words, for which we fail to reject the null hypothesis, then that is a type 2 error. On the other hand, if the null hypothesis is false, and we get a hold of a data set that leads us to conclude that it's false, then that is a correct decision. So this is just a nice way to organize this, and I think it helps to understand perhaps a little bit better what these different kind of errors are and what the four possible situations are. Now, obviously, we don't want to commit a type 1 error, and we don't want to commit a type 2 error, right? We would like to always come to the correct conclusion. If the null hypothesis is true, we want to conclude that it's true. And if the null hypothesis is false, we would like to always conclude that it's false. But in any real-world situation, there's always the possibility of our being in any one of these four scenarios before we conduct the experiment. All right? And so what that means is that there's always the potential that we'll either commit a type 1 error or a type 2 error prior to conducting the experiment. Those possibilities are available, all right, or possible. And because of that, we're going to define some notation to represent the probabilities associated with these two types of errors. And so we will let alpha represent the probability that, and it's a conditional probability, by the way. So alpha is the conditional probability that we conclude that the null hypothesis is false given or when the null hypothesis is actually true. All right, so alpha is the probability of a type 1 error. On the other hand, beta is the conditional probability that we conclude the null hypothesis is true given that the null hypothesis is false. Now, alpha, the probability of a type 1 error, is also called the significance level of the test. And the significance level of the test is something that you as the researcher have control over. You are the one who will determine or decide what significance level that you want to use in evaluating your data. Now, another characteristic of a hypothesis test is the power of the test. Now, the power of a statistical hypothesis test is the conditional probability of correctly rejecting the null hypothesis. In other words, concluding that it's false when in fact it is false and therefore should be rejected. Again, the power of a test, it's a conditional probability, and it's the conditional probability of rejecting the null hypothesis when that null hypothesis is false and therefore should be rejected. Now, power depends on several quantities, such as the sample size used in the test or for sampling the population, the level of variation associated with the response variable in the population, and the significance level being used in the test. So power is not a single value. Power is a function, and it's a function of several quantities. It depends on a number of different things. And so going back to our two-way table here, all right, we can drop in this notation that shows us where these different quantities lie. So if we go back here, again, this cell corresponds to a type 1 error, and the probability of a type 1 error is denoted by alpha. Likewise, this cell here that I'm circling corresponds to a type 2 error. Remember, when the null hypothesis is false, but we conclude that it's true, that's a type 2 error. And the probability of committing a type 2 error is beta. Now, in this lower right corner, so corresponding to the situation where the true state of the null hypothesis is that the null hypothesis is in fact false, and we conclude that it's false, the probability of that particular type of correct conclusion, that is called the power. So these cells here, these three cells, show us where alpha, beta, and power lie. And then I would also point out that the columns have to add up to 1. And so based on that, the probability of this type of correct conclusion, where the null hypothesis is true and we don't reject it, we conclude that it's true, the probability of that situation is 1 minus alpha. Now, given that the columns must add up to 1. All right, we have this nice relationship that relates power and beta. And so power is 1 minus beta. Again, the definition of power is that it's the conditional probability that the null hypothesis is rejected when in fact the null hypothesis is false and should be rejected. All right, that is by the complement rule equal to 1 minus the conditional probability that the null hypothesis is not rejected when in fact the null hypothesis is false and should be rejected. And that conditional probability is just beta. So power is equal to 1 minus beta. Now, we could also express this as the sum of power and beta being equal to 1. And that's really what we said back here on the previous slide with this two-way table. The columns have to add up to 1. And so in this case, in this last column, that would mean that beta plus power is equal to 1. Now, because power and beta are related according to this relationship, and since power is a function of many things, including the sample size, the level of variation in the population, the significance level of the test, and so forth, that implies that beta is a function of those quantities also. So beta, the probability of a type 2 error, is not a single number. It's not a single value. It's a function. It depends on, again, the sample size, the level of variation in the population, the significance level being used in the test, and so forth. So whereas alpha is a single number that is set by the researcher, all right, beta is a function of these other quantities, including the significance level. Now let's think about the relationships, additional relationships between alpha, beta, and power. For a fixed sample size, alpha and beta are inversely related. In other words, if alpha decreases, then beta increases. If beta decreases, then alpha increases. Another way to say this second bullet point would be to say that if we increase alpha, then we will decrease beta. Now, for a fixed sample size, alpha and power are directly related. In other words, if alpha is decreased, if we decide to use a smaller significance level, then we will be decreasing power. On the other hand, if we increase alpha, if we use a larger significance level, then the power of the test is increased. Now, ideally, we would like alpha and beta to be 0. Remember, alpha is the probability of a type 1 error. Beta is the probability of a type 2 error. And ideally, we would like both types of errors to not occur at all. We would like for there to be no chance for those two types of errors. And so that would mean that alpha and beta are 0. And if beta is 0, then that implies that power would be 1. All right? Now, what does that correspond to? A power of 1? Well, remember that the power of a test is the probability of rejecting the null hypothesis when the null hypothesis is false and should be rejected. So it's that probability of correctly rejecting the null hypothesis when it should be rejected. And so having a power of 1 says that we would always reject the null hypothesis when we should. Now the problem is that in any realistic test, there's always the potential for a type 1 error. There's always the potential for a type 2 error, and therefore power will always be less than 1. Okay? But now recognizing that, if we can't have the ideal situation where alpha and beta are both 0, we would at least like them both to be small, that is close to 0. And therefore, that would give us a power close to 1. But remember, let me go back to the previous slide, we have this inverse relationship between alpha and beta. In particular, for a given sample size, if we choose to decrease the significance level, in other words, if we decide to make the probability of a type 1 error smaller, then we will necessarily be increasing the probability of a type 2 error. Conversely, if we decide to decrease the probability of a type 2 error, then what would happen is, for a fixed sample size, that would require making the probability of a type 1 error bigger. So we would like for both alpha and beta to be small, as close to 0 as is reasonable in a given situation. But again, for a fixed sample size, we have this inverse relationship between alpha and beta. For a fixed sample size, we can't make both alpha and beta small. In order to make them both small, and in particular, once we've set alpha at the desired level, in order to make beta smaller, then what we've got to do is we've got to increase the sample size. That's really the only way to accomplish that. Now, increasing the sample size can be thought of as getting more information from the population about the population. And so it makes sense that if we obtain more information about the population, then beta, the probability of a type 2 error, would decrease. So that is how we can make both alpha and beta small. Remember, alpha is set by the experimenter. It's the significance level that you choose to use for the test. In order to make beta smaller, we've got to increase the sample size. So these are important characteristics of a hypothesis test. Alpha, the significance level of the test, which is the probability of a type 1 error. Beta, the probability of a type 2 error, right, which is when we fail to reject a false null hypothesis. And then finally, the power of the test, which is the probability of correctly rejecting a false null hypothesis. So these are characteristics of tests, and we've quantified the probabilities of these various characteristics. We see the relationships between these characteristics, and we see that if we want to make both alpha and beta small, then we have to increase the sample size. And if we are able to make beta smaller, then that will make the power of the test greater.